When we look at something like this, then NH3 is called a ligand, and ligand is basically Lewis base that can donate pair of electrons. This whole thing is a complex, AgNH3 whole twice plus. So we have metal connected to some ligands, and ligand is electron pair donor. Plus is the charge total on this system. The area of space encompassing the ligand and the metal, that is called coordination sphere. So this bracket is important. If you take something out of the bracket, that means you are making alteration to the coordination sphere. So that can be a type of isomerism actually, bringing something inside that square bracket or taking something outside the square bracket. If you look at a metal alone or not alone, then we notice differences in some properties. Ag plus to Ag reduction and ERP is around 0.8, and here also it is getting reduced Ag. From +1 to 0, it's the same change. But you find that here the value is different. So it shows that the presence of ligands here, Cn, that is ligand. Presence of ligands can alter the properties. Most metal ions in water, we say H plus in water lives mostly as H3O plus, and there are some other forms as well. So that shows H plus is able to attach itself to oxygen. H plus is very small, but even metal is able to attach itself to water. So in most cases you find this situation, metal H2O6, and then certain charge on this whole thing. Charge in the total system will be the sum of individual charges. That's straightforward. Inside ligand doesn't look like an individual atom often. Ligand could be a group of atoms. So out of the group of the atoms, some atom must be connected directly to the metal. So inside the ligand, there is one atom which is bonded directly to the metal. That is called the donor atom. Coordination number. Number of ligands attached to the metal. This can be refined a bit. This can be refined a bit. The number of ligand atoms attached to the metal. Because in some ligands, there are multiple atoms present. In some ligands, there are multiple atoms present that can be connected to the metal, right? So it is more appropriate to say number of atoms inside the ligand that are connected to the metal. That is coordination number. Sometimes it may be equal to number of ligands themselves, and sometimes it may be more than the number of ligands attached. Mostly you come across coordination numbers or CNs equal to 4 and 6. Also, there are certain geometries that you come across often. And these are tetrahedral, square planar, octahedral. And they are related to these 4, 6. If coordination number is 4, then the geometry is either tetrahedral or square planar. Normally you see this case with D8 metal ions. And if Cn is 6, then it is octahedral geometry. For Cr3+ and cobalt 3+, coordination number is always 6. Always 6. Now, if you compare fluorine with chlorine, then fluorine is smaller in size. You find that a complex like this is able to form, but stability-wise, this one is stable. So F and Cl difference is there in the behavior. Here you have got NH3, here you have got Cn. NH3 is basically neutral species. NH3 is neutral. Cn has got -1 character. So charge. So these things influence some of the things, and that is very much understandable. NH3 and Cn-, there needs to be some behavior difference due to neutral versus charged ligand, size of the ligand F or Cl. Coming to nomenclature, now we should be focusing on mononuclear coordination entities. mononuclear. Mononuclear means single central metal atom. Otherwise, you can have more than one central metal atom also. For salts, this thing is salt. This is complex having +2 charge, and then you have got Cl -1 and -1. Name the cation before anion. Cation is a complex. Now, cation comes before anion, but you have to tell which cation it is. So to name a complex ion, ligands are named in alphabetical order and before the metal. Ligands in alphabetical order. You see, sometimes there can be multiple ligands, like in this example, ammonia is a ligand, and then Cl also. So you may have multiple ligands. So you just need to look at alphabetization when there are multiple ligands. So you have got this A, NH3, amine type of behavior. A, then C. C comes after A, right? So that takes care of this part. And then you say cobalt, metal. Now, this fellow has come 5 times, so that penta you add before A. And then you need to tell the valency of cobalt. That you can easily find. It's like oxidation number. So you can take X for cobalt, ammonia 0, C -1, and equate it to 2. So that thing is written here. This penta or whatever, that is not considered in alphabetization. Anionic ligands. Ligand is electron pair donor. Well, neutral things can also donate, and anionic things can also donate. So ligand can be anionic or ligand can be neutral. If ligand is anionic, like Cl-, then anionic ligands end in O. Chloro. And neutral ligands are just the names of the molecules. There may be some exceptions. For example, water is not called water. It's called aqua. NH3, not ammonia, amine. Here is some list. anion, 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 anion. Up to here, all anions. Azido, bromo, fluoro, cyano, hydroxo, carbonato, oxalato. Neutral molecules. This is not called ammonia, amine. Then this one, very common, EN or ethylene diamine. Diamine. Earlier I was saying that sometimes inside the ligand there may be more than one atoms that may be willing to donate. You will see such cases. Pyridine is just pyridine. Water is aqua, not water. Now we discussed this point. Look at this. NH3 coming 5 times. So it was penta. But what about this situation? Ligand name has Greek prefix already. What if the ligand name has Greek prefix already? In this example, ligand name amine did not have any Greek prefix. So no problem. But sometimes, as I told you, that inside the ligand there can be 2 atoms that are willing to donate. There are things which are not as straight as ammonia or Cl. And it is possible that in the name of the ligand itself there is di something or tri something. So we don't do it like this, penta, di type of thing we don't use in that case. So if ligand itself has got something Greek in it, di, tri type of thing, in that case, what we do is, I think example is best. Say for example, this ligand is called ethylene diamine, di. So there's a use of di, tri type of thing. Now we won't put tri and say triethylene diamine. Instead of tri, we rather use tris. And we put this thing in bracket also. So this tree is tris, then this En is called ethylene diamine. Bracket close. And then metal. Then it's oxidation state. That's the complex part. and then this part, anion. Cation before anion. Cation and then anion, chloride. Now in this example, complex was cation. Anion was not complex. Anion was just chloride. If complex is anion, then name ends in 8. Oxidation state of metal is given in Roman numerals in parenthesis at the end of the complex name. So in case of anion, name ends in 8. So if you want to give name to this complex, cyano, minus charge, so O sound, dicyano, silver. Now you could have called silver had it been cation, but now you will have to use 8 sound, argentate, then 1. So this is how you name this anion. If you want to name the whole thing, cation, you know how to name this complex. Cation's name will come before. So di, amine, silver, valency, oxidation state. Here also oxidation state 1. That should be it for this part. You very well know the meaning of isomerism. So in this context, when we talk of isomerism, then there will be different structure possibility and there will be different spatial arrangement possibility. So broad categorization will be 2, structural, spatial or stereo, and that's a broad classification. In case of stereo, bonding is same. You have geometrical and optical, and here you have got coordination sphere isomers and linkage isomers. This is just broadly speaking. This is just broadly speaking. I can possibly add 2 more here. Coordination, linkage, ionization, isomerism, solvate, isomerism. Ionization, isomerism, solvate, isomerism. So 4 here and 2 here. Let's talk about linkage isomers. Ligand can link to the metal in different ways. Imagine a ligand NO2 minus. It can connect to metal via nitrogen, or it can connect to the metal via oxygen. Right? If you consider this complex, one central atom, two types of ligands. Okay, ammonia will connect in one way only, nitrogen part, but this can connect in two ways. Now this fellow is nitrate if it links to cobalt via nitrogen. Then it's called nitro. Via nitrogen, nitro. But when it links via oxygen to cobalt, then it's called nitrito. And they look different in color. So what would be the name of this fellow? Pentamine part is okay. Cobalt 3 part is okay. But this nitrate part, that can be different. This can be called nitro in one case and nitrito in another case. Look at this cobalt connected to 5 amines. One point. So that 1 point which is left, the 6th one, it connects via nitrogen, it connects via oxygen. And you've got isomers. Here is another example. This ligand can link through sulfur or nitrogen. Coordination sphere isomerism. Coordination sphere isomerism. Now I was talking about coordination space earlier. Coordination sphere, that's the space encompassing the ligands and metal ion. And I was saying something can come in, something can go out, and that should make a difference. There you are. Look at this, CrCl3H2O6. Inside the bracket something, outside something. One Cl is brought in. That makes a big difference, violet versus green. One more Cl brought in. And of course, water is brought out also. So this complex is changing, but the whole formula is not changing. And change in that complex itself is bringing about such changes. So would you like to try out the name, IUPAC name for this thing? What are the ligands? Amine, water, which is aqua, and chloride.
Sir, it's tetraamine, aqua chlorido, cobalt 3 chloride.
Cobalt 3 chloride. M comes before Q. So tetraamine, then aqua, then chlorido, yes, chlorido, then cobalt, then 3 chloride. That's right. How about this?
Sir, it's potassium 2, tetrahydroxy, zincate 4.
Potassium is not in the complex. When metal is inside the complex, then you tell its valency. Complex is anion here. Potassium will be just potassium.
So it's potassium tetrahydroxy, zincate 4.
Potassium tetrahydrox. It is an anion charge. So just like chloro, hydroxo, potassium tetrahydroxo, zinc, but this is anion, so zincate, right? Zincate And what's the oxidation state of zinc?
2.
Zinc, potassium plus 1 into 2 plus X plus minus 1 into 4 equal to 0. 2. Potassium tetrahydroxo zincate 2. Any questions? Let me know. What about this?
So let's try oxalato. It's potassium trioxalato, eliminate 3.
Potassium trioxalato, aluminum 3 is right. What about this one?
Sir, it's tetracarbonyl nickel.
Tetracarbonyl nickel, 0.
Sir, it's pentaamine carbonato cobalt 3 chloride.
Pentamine carbonato cobalt 3 chloride is correct. Try this.
So this is dichlorido bis triphenyl phosphine nickel 2.
You said chlorido.
Yes, sir. Sorry, chloro.
Chloro. Can you repeat then?
So this is dichloro bis triphenyl phosphine nickel 2.
Yes. And there will be bracket for triphenyl phosphine. So dichloro bis, then bracket triphenyl phosphine, then nickel 2. Well, there are various names used for this thing, En, then this. They're all in use. But from IUPAC perspective, I would recommend this one. But you will find several of them in use. This one is what I would recommend. Now, when we were discussing this, you said initially dichloride. While dichloro is used quite a lot for this, but is it really wrong to say dichloride? I don't think it is entirely wrong to use chlorido, but chloro looks easier. After all, Cl is Cl minus here, chloride, chlorido. So what would be the name of this fellow?
Sir, it's dichloro, bis, ethene 1,2-diamine, cobalt 3.
Can you repeat?
Sir, it's dichloro, bis, ethene 1,2-diamine, cobalt 3.
Ethane 1,2-diamine.
Sorry, ethane 1,2-diamine.
So ethane 1,2-diamine, then cobalt, how much?
Cobalt 3.
Okay.